Okay, so last time we were together, we were talking about the detection of extrasolar planets using the Doppler method. And I want to talk about another way that we're currently finding extrasolar planets, which is actually leading to way more discoveries than we've had with the Doppler method. And that's using what is known as the transit method. So this is a graph, and on the horizontal axis of this graph are different years, going way, way back, more than 20 years now, looking at the time when we found different extrasolar planets. And the height of the graph tells you how many extrasolar planets we had found on a particular calendar date or year. And what you'll see is over most of the last 20 years, we found very few planets. Only a couple every year. Only a couple every year. Then we started to find a few more, and then all of a sudden you see this dramatic increase in the number of planets we found. And that's because a particular space telescope, known as Kepler, became active and started producing data, finding extrasolar planets, using this method known as the transit method that I'm going to teach you about today. So I just wanted you guys to leave this class knowing how we're, in a modern sense, using a space telescope to go hunt for and find many, many, many more planets in our local part of the galaxy. So when we detect extrasolar planets with the transit method, I want you to think about it. We just had a solar eclipse here on Earth this year, and I just want you to think about that was an occasion where the sun's light was being blocked as an object moved in front of it, an eclipse. Essentially, that's what's happening with the transit method. A star in our galaxy that we're looking at, its light becomes slightly dimmer as a planet that's orbiting that star moves in front of it. So the transit method is like watching eclipses in other solar systems using this amazing telescope. So when a star is orbited by an exoplanet, a planet outside of our solar system, that planet moves in front of the star and causes the star's light to dip or become slightly dimmer for a small period of time while the planet's in front. And then as the planet moves away from being in front of the star resumes its normal brightness, and it's that dip that tells us whether or not a planet is there. So we'll be looking at graphs of a star's brightness as a function of time and looking at how the dips tell us whether or not planets exist. So I want you to think about the light from the star and how it'll be affected. I've just kind of described it in words. I want you to start as I show you different kind of examples here. I want you to think about what that graph's going to look like of a star's total brightness versus time. So the big orange dot or yellow dot in this class is always a star, sun. So there's your star. Is it the sun, though, if it's an extrasolar planet that we're going to look at? No. So that's some other star in our galaxy. And you have a planet. Okay. And right now, if you were looking at this system, how much of the star's light would you be receiving? All of it. So think about that graph for a minute. You have all of the sun's light, and you're still getting all of the sun's light, and you're still getting all of the sun's light, and you're still getting all of the sun's light. And then all of a sudden, what if the planet were moving, and it got to this point? At this instant in time, that total amount of light you're getting from the sun, if the planet continues to move a little bit, is going to start to become less. And it's going to take a little bit of time for the planet to move across the first edge of the star and move inward until it's all the way covering the star. So there's going to be an amount of time that it takes for the total brightness of the star to decrease to where it's now being blocked by that planet, by the most the planet can block, because it's completely in front of the star. Now the planet's going to move across that star over some amount of time. So keep thinking about how that graph looks, what it looks like now as the planet. And let me just ask you this. Is it blocking more light now than it was just a second ago, or the same amount of light? Same amount. And it's still the same amount, and it's still the same amount, and it's still the same amount until then. As the planet just starts to move so that it's no longer blocking any of the star's light, the graph will start going back up, indicating that now you're getting more and more of that total amount of the star's light until it's no longer blocking at all and it's back to that original amount of starlight. So I want you to think about how that graph looks, and I want to show you kind of what it would look like in real time to watch that happen. So when we look at a star and we see how the brightness of the star changes over a period of time, we can make this graph. And in the graph, there'll be changes in brightness, and I'm going to call that place where the light goes down as a result of becoming less and less because the planet is blocking that. I'm going to call those dips, a dip in the brightness of the star. So we see dips in this graph to indicate that there's a planet there. So here's your star again and your planet and a graph in real time. And you can see that the light becomes dimmer as the planet moves, but it stays the same value while the planet moves across the surface of the star and then goes back up as it transitions back out. So that's sort of the characteristic shape of a dip that we would see in one of these graphs. Now, imagine the planet goes all the way around and comes back. You'd see another dip happen later in time if you could watch it long enough, and the planet's orbit was short enough in time that you could watch more than one dip happen. We don't always get to see that, but sometimes we do. So planet features. There's two important properties of planets that we can determine by looking at these dips in the star's light. The first one is you can know the size of the exoplanet. So the size or depth of the dip will tell you the size of the exoplanet, and the time that it takes for a dip to occur will tell you how long it takes the planet to go around its star. I'm going to say both of those again. So you've got two things, the depth of a dip, and the depth of the dip tells you how much light's being blocked, and that also tells you how big the planet is. Bigger dip, bigger planet. Deeper dip might be a better way to say that. Deeper dip, bigger planet. The width of the dip, how long it takes for the star to first start becoming dimmer as a result of this eclipse of the planet until it comes all the way back up, that's the width of the dip. That can tell you how long it really takes the star to go all the way around. If it takes a long time to make a dip, that star's not moving very fast, or that planet's not moving very fast, that must mean it's a long ways away. So the width of the dip tells you some things about how long the orbital period of the planet must be. And the other is that the sides of the dips aren't perfectly straight up and down, they're sloped slightly, telling you that it takes a little time for the planet to move all the way in front of the star and then move back out so that it's not blocking any light at all. And the last thing is the bottoms of the dips are flat, indicating that it takes a little time for the planet to move all the way across the star. Stars are much bigger than planets, so it takes a little while for that planet to move all the way across the star, and therefore the dips are flat. Okay. So here's an example of repeated dips being observed of a star. And I just want you to kind of notice some of those features. You've got all of this idea of timing between dips to now kind of think about, like when a dip happens and then it goes back to its original brightness. So a dip has happened and it goes back to its original brightness, and then a dip starts again. I want you to think about what the planet's done in that time. So this was the instant when the planet first started to move in front of the star. This is the instant when the planet then leaves from being in front of the star, and then it goes all the way around the star, and then a new dip happens. So from this instant in time to that instant in time is one full orbit. That's the period of the orbit. So if you're looking at these graphs and some kind of time is indicated on here, and I ask you, how long did it take the planet to go all the way around? You have to kind of find that beginning of an orbit and the beginning of a dip, and then the beginning of a next dip to kind of determine the total amount of time of an orbit. Okay, so also notice, and I didn't draw this too well on this graph, the length of the time here is much longer than the width of just one dip. Because this is just the width, the amount of time that it takes to make one dip is just the time where it was in front of the star. But this is the amount of time that it takes to go all the way around and come back and be in front again. So in theory, this should be a lot longer than just a dip width. Okay, so I have a question that I want you guys to think about, and go ahead and talk to each other about this. I'll give you guys just a minute, and then I'll come back.
So it's done transiting. So it's not
So-
from the start anymore.
So it's right after when it was in front?
Yeah, yeah. So wouldn't that be C, right?
Yeah, because it's in front of the star B, and then so the next part after that. Yeah, cool.
All right, you guys want to vote? Give it a shot. All right, let's vote on 3. Which of the letters do you think it is? 1, 2, 3. Hey, nice job. Right answer?
C.
C. Okay, good. Let's talk about this for a second. So one of the things that you need to recognize when you look at a question like this is where I indicate Earth is, because that's where you're observing from. And by knowing that, let me just ask you this. Which of the letters corresponds to when the dip was happening? Which of the letters best corresponds, which of these letters best corresponds to when that dip was happening?
B.
B, yeah, okay. And it's a time after B, known as C. Good job, okay. So I'm showing you the simple case of one planet. What if instead there are multiple planets? So each planet is going to make its own dip. And in this case, I've shown the case where all the dips happen and never overlap. But that might not always be the case. But let's just think about this. This pattern of dips lets you know some things about the planets in a system of planets around a star, a solar system. If this was what we knew about that solar system, I just want you to kind of look at that pattern really quick. How many different planets might be in the solar system, do you think?
2.
2, yeah. One of them is big, and the other is smaller. And you could start even looking at the timing between the dips and the widths of the dips and start knowing some things about which planet is closer or farther from the star based on the kind of things we were just talking about. So I want to show you an example of what this might look like physically. You could have a star and a small planet that moves in front of that star, followed by a big planet that moves in front of the star afterwards. And I want you to start thinking about that graph that would come from looking at this system. And I'm going to play this a couple times. I want you to start noticing which object appears to be moving faster or slower. Thinking about, again, which one's the big planet, which one's the small planet. So think about that graph. I'm just going to ask you, if you're looking at the graph, which dip is going to occur first? The shallow dip or the deep dip for this system? Which dip will you see first in the graph? The shallow dip or the deep dip?
The shallow
Shallow.
one.
Shallow one for the small planet. Which dip is going to appear wider? The one for the small planet or the one for the big planet?
The small planet.
And that's because it's moving
Slower.
slower. Good. Okay, cool. So you might get a graph for that planet that looks like you were just describing. But what if you had this case instead? What if you had the case of two planets whose motions, so I'm going to go back a slide, two planets whose motions happen so that the planets are simultaneously in front of the star. They're in front of the star at the same time. So in this case, I want to kind of talk you through what the graph might look like, because it could get kind of complicated because both dips are happening at the same time, so they're not drawn, or you wouldn't see them in your data independently, you'd see them overlapping. So imagine that you have this case where the first thing you see is all the light from the star, then you see the light start to dip and go down to some value that's the shallow dip, if you will. And it's going on for a little while, and then all of a sudden it starts to get deeper again. And it gets deeper by quite a bit, indicating that a bigger planet has come into the game, making it even less light than you were looking at before. And that happens for a while. So you have a strange shaped dip with two different dips in it that goes on for a while. That's an indication to you that more than one planet is blocking starlight. And then all of a sudden, both planets emerge off the, so that they're no longer in front of the star, and the dip goes up to its or the brightness of the star goes up to its original value. So that's a complicated thing. And what if it happens over and over? And sometimes they're exactly in front together, and sometimes only one of them is because they have different orbital periods. I want you guys to be able to analyze complicated graphs like that. So let me just say that when two exoplanets are overlapping or crossing in front of the star, you might get these complicated shapes of dips. And you're going to have to be able to kind of look at the graph and figure out when is the dip occurring due to the small planet and when is the dip occurring due to the big planet. So the top graph is every single dip that might occur for the small planet and the big planet drawn separately. So the reddish colored dips are much deeper, and they go with the bigger the small planet.
Big.
And the the green dips are shallower and go with the small planet. I want you to notice a couple other things. Which one's wider, the green or the red?
Green.
So which of those two objects, the big planet or the small planet, is further away from its host star? The big planet or the small planet? Which one's further away from its host star?
The smaller one.
Yeah. Wider dips happening less frequently. Must be further away. At this time interval, that was the case that I just showed you in the video, where you had a period of time where the small planet had moved in front of the star and was blocking all of the star's light, and then all of a sudden the big planet comes along and is now also in front of the star, making a dip that is the combination of both of these simultaneously. And that's represented in the real plot that we would get, which looks more like this. So this is what we would get as data from this system. You'd have this weird shaped dip going, that's not just one planet. That's both a small planet making a dip over some period of time and a big planet making a dip simultaneously. And there's times where those two planets' time might overlap just perfectly, so you get one of these really big dips that's bigger than either of them separately. And so your ability to kind of look across the entire time and notice these different patterns of dips that might be happening is how you'll determine whether or not there's one or two planets in front of the star. So I want you to work on this together. Just think about which things you'd use to fill in this blank, and then we'll debrief it in just a second.
Exoplanets that are closer to the parent stars are detected more easily, so they're closer, yeah. Because the dips that cause them to brightness of their parent star occur
More frequently.
when it's closer, yeah.
Yeah.
Than the dips caused by the planets further from their parent stars. The smaller ones, what is that?
Less.
Less, okay.
Yeah.
Shallower.
Shallow.
Yeah, in the observed brightness of the parents. possible, because we just saw this,
Possible.
yeah,
Oh,
in
yeah.
the last graph too.
They
so-
just merge into the same.
Yeah,
dip.
yeah, okay.
Okay, it looks like you guys are ready. Let's go ahead and debrief this together, shall we? So exoplanets that are close to their parent stars are detected
More.
more easily because their dips that they cause in the observed brightness of the parent stars occur more frequently than dips that are created by planets that are further away. Okay. Exoplanets that are smaller are detected less easily because they create shallower dips than in the observed brightness of their parent star than larger planets. So it is or is not possible.
It is
It is
possible.
It's possible to detect multiple planets, yeah, and that was what we just saw in that last graph. Okay, great. So what I want you guys to get ready for again is one of these whiteboard activities where you're going to be asked to create representations for extrasolar planet systems and draw your own curves and your own systems that match sort of the criteria that are in this activity. So next you'll get your whiteboards and we'll be coming around to check your work in just a little bit. Nice job.